Okay, this is a worked paper, a CIE mechanics paper from March 2022. I'm going to work through these. I won't dwell on the calculations very much, just concentrate on the principles and the approach. And if you want to pause the video and just look at any more detailed calculations to satisfy yourself, then that obviously is fine. I'm going to do this in two parts. I'm going to do the first four questions on one video, and then the remaining three on a subsequent video. So let's have a look at this first one. A crane is used to raise a block of mass 600 kilograms vertically upwards at a constant speed through a height of 15 meters. Resists the motion of the block, which the crane does 10,000 joules of work to overcome. Find the total work done by the crane. Okay, yeah, it sort of represents it here, but the main thing really is, and I can't stress this too much, is this equation here. It's the sort of positive work done to a particle less the resisted work is going to be equal to the increase in kinetic energy plus the increase in potential energy. This right hand side we refer to as mechanical energy. Now, very often the terminology around these in some of these questions can be a bit confusing. We often see this increase in potential energy being referred to as work done against gravity, which I think is a bit of a confusing concept. We basically apply work to a particle and it results in changing speed and changing and or change in height. And I think if we stick to that sort of structure, then these problems are a lot easier. So let's have a look. What do we want? Well, this is what we want. This is the work done by the crane. This is the positive lifting work that it's done. We've got a resistance of 10,000. Okay. The increase in kinetic energy, 0, because constant speed, so the velocity doesn't change, so the kinetic energy doesn't change either. And meanwhile, we have lifted it through 600 kilograms against gravity. Got the gravitational constant in there, times 15 meters, mgh, potential energy, isn't it? So we just got an equation in W there, and that's going to give us W equals 100,000 joules. Right, okay, so that's the first part. The second part, given that the average power exerted by the crane is 12.5 kilowatts, 12,500 watts, so sometimes given in kilowatts, we have to be careful and make sure that we convert it correctly and multiply by 1,000. Find the total time for which the block is in motion. Well, I mean, if we look at this basic definition of what power is, it's the rate of doing work, then that gives us a very simple equation. That's the power, that's the work, which we calculated in part A, and the time, that's going to give us time. It's equal to 8 seconds. So that power is being exerted over a period of 8 seconds to do that lifting work. So that is number one. Number two now. All right, a particle P is projected vertically upwards from horizontal ground with speed u, reaching a maximum height of 20 meters above the ground. Find the value of u. Okay, as with many of these things, you know, some of some things are kind of buried in the language, in the narrative. P reaches a maximum height of 20 meters above the ground. Okay, so what we've got is a constant acceleration kinematics problem for this part, where we know, let's have a look, this is the equation we're going to use because we know, well, V is, because it's going to be 0, the maximum height of 20 meters. U, we're trying to find, A is acceleration due to gravity. Now we're thinking upwards, so therefore it's going to be negative, it's going to be -10. So very important to actually make sure that you establish your frame of reference, which direction is positive. So usually upwards and to the right of what we tend to use by convention. The distance or displacement being the same thing on this one is 20. Yeah, the final velocity 0. So yeah, plug those in and we get to u equals 20. That's straightforward. Now the second part, find the total time for which P is at least 15 meters above the ground. This is we're talking about displacement here, aren't we? 15 meters. So we're interested here in our sort of our main displacement Suvat equation, which is S equals ut plus half at squared. So we want that displacement. We're interested in the values of t for which that is greater than 15. All right, so given that, if we just rearrange this, make it look like this, then this, then we're basically solving a quadratic inequality. We generally have to be a little bit careful about signs when we're doing this, but I think on this one, we've got it factorized, and it's probably easy to see that if we've got a value of t between 1 and 3, then this will be negative, because one of these will be, one of these factors will be negative, the other one will be positive. So so there we go, between 1 and 3, and that means that the total time is 2 seconds. Okay, so that is that one. So that's a kind of fairly straightforward Suvat kinematics problem. Right, number 3. Okay, we're back to work and energy on this. A car of mass m kilograms is towing a trailer of mass 300 kilograms down a straight hill inclined at 3 degrees to the horizontal at a constant speed. There are resistance forces on the car and the trailer, and the total work done against those forces in 50 meters is 40,000 joules. The engine of the car is doing no work. Interesting, so kind of coasting down there. And the tow bar is light and rigid. Find the value of m. All right, so we're going to, we're looking at this equation again. So the total work done is the change in mechanical energy. So the work done, the sort of positive work done by the sort of the you know, the power unit, the engine or whatever, plus the work of resistance. Well, this is going to be negative on this. I've written as a positive on this, but it'll just come out as a negative. Is going to be a change in kinetic energy plus the change in potential energy. Well, what are these two? Well, the change in kinetic energy, well, constant speed. So, so there is no change in kinetic energy. That is 0. The change in potential energy is basically this distance that we're coming down. So as we're traveling 50 meters down there, then we want this. This is 3 degrees. So basically, that is going to be 50 sine 3. Okay, so the change in potential energy is going to be the total mass, car and trailer, g times the height that we've come through, and of course that is negative as well. We've actually lost potential energy in this process. So our resistance force, which is minus 40,000, resistance, the work done is going to be minus 40,000. That's what we're given there. So we've got our equation here: minus 40,000 equals this this reduction in potential energy. And yeah, so we've got an equation there. It's purely in m, so we can just do a bit of manipulation on this, and we're going to work that through to m equals this figure, 1,228.59 kilograms. I think that's to 2 decimal places. Yeah. Right. Okay. The tick, by the way, isn't some kind of self-congratulation. That was basically, it means it's been checked against the mark scheme. B, find the tension in the tow bar between the car and the trailer if the resistance force on the trailer is 200 newtons. Right, so in this case now we kind of know the forces. We're just thinking Newton's second law of motion here. We don't have to think about kind of changing kinetic energy or anything like that. So if we just consider the trailer, so we kind of draw, a line around this. We've got the tension pulling it down. We've got a resistance force pulling it back. Right. Well, and the other thing is on here is we've got the resolved part of the weight actually coming down the slope as well. Not drawing it in, but that's what's coming down there. So now we're still at constant acceleration, constant velocity here, so zero acceleration. So therefore, the net forces net out to zero. So the forces down the slope are going to be the tension pulling it down. This is the weight resolved down the slope, and that's going to be equal to the force of resistance. Okay. So again, equation just in T, that works through to 43 newtons, 43.0 to 1 decimal place, 43 newtons. Okay. Okay, so this is a sort of common theme really, is that, when you have got something that's not moving, very often on the point of moving, or it's actually moving at constant velocity, then since there's no acceleration, if we think about Newton's second law of motion, F equals ma, then the right-hand side of that equation is going to be zero. So therefore, the net forces have to equal zero. That's what we've got here. Okay, so that's number 3. Okay, so number 4. The total mass of a cyclist and her bicycle is 70 kilograms. Riding with a constant power of 180 watts up a straight hill at angle alpha to the horizontal, sine alpha equals 0.05. At an instant when the cyclist speed is 6 meters per second, her acceleration is minus 0.2 meters per second. And there's a constant resistance of motion of F. Find the value of that F. Okay, so this cyclist is going uphill. So by convention, I tend to write if there's motions going to the right, then or the motion is going, normally think of the positive direction in the right. So if the cyclist is moving to the right, then it makes sense to draw it this way around rather than the sort of mirror image. We don't know 30 at this point. But we can easily calculate that from what we're given. So at 6 meters per second, well, this is the equation that we're interested in. So we're very often interested in thinking of power in terms of force, something like driving force, and the velocity. And that's just what we've got here in this. So we've seen earlier in the paper, power equals work divided by time, but we can restate that like this. And to be honest, this turns out to be more useful, if you like, we'll see it more often, is expressing power in terms of velocity and force in these kind of questions. So so that force is going to be equal to the power of 180 watts divided by 6, which is meters per second, giving us 30 newtons. So that is the driving force of the cyclist up this incline. So now what we've got, at a constant 6 meters per second, the net force is going to be 0. So so the weight resolved down the slope is going to be 70 g sine alpha. So if you're not familiar with the idea of resolving weights and so on down slopes, then you might want to check out mine or anybody else's video on resolution of forces. But that's what we've got. So we've got this this 70G sine alpha, which is what sine alpha is here, 0.05. So that means that this force is 35 newtons. That's the weight resolved down the slope. Okay. So effectively the weight is kind of pulling the cyclist back by 35 newtons worth of force. Right, so if we look at the Newton's second law of motion, then the net force is equal to the mass times the acceleration being a deceleration in this case, minus 0.2. So that driving force minus the kind of that's the pushing up force, and this is the pulling down force. So we've got the resistance to motion, Fr, and we just that's what F is in the problem statement, plus the weight resolved down the force. So both of these two things are kind of resisting. There's friction, probably this, isn't it? And then this is the weight. So our driving force has got to overcome both of these. Well, clearly it's not going to be able to do that because it's decelerating. So our driving force of 30 newtons minus the friction, if that's what it is, plus 35 is going to be equal to minus 14, and we can just work out the resistance force from that, giving us 9 newtons. Okay, so that is the value of F. Right, find the steady speed that the cyclist could maintain up the hill when working at this power. Right, so that's driving force. Well, at constant speed, then again, no acceleration. Okay, so so net forces are 0. So the driving force is going to be equal to the resistance force, friction, air resistance, maybe. Plus the resolved part of the weight down the slope. So those are going to be equal. We know what this is, certainly in terms of V, 180 over V. That's our equation here. So the force will vary according to the velocity, won't it? And the resistance force we calculated to be 9. The result part of the weight of this is this 70G sine alpha, where sine alpha is 0.05. So we can just substitute those values in there, rearrange to get V equals this, which turns out to be 4.09 meters per second. Okay, so hopefully that has been useful. Right, okay, so we'll stop there and we'll think about part B in the next video.